In this short video, we'll show that energy can be considered to have particle-like properties or wave-like properties. So we know that E equals h nu, so energy is proportional to frequency. We also know that speed is distance times by time. So a way to look at that in terms of energy is that the speed of light, for example, c, is distance. Well, distance can be a length, and particularly we're interested in a wavelength. So we call the wavelength L, the Greek letter L, which is lambda. And time is 1 over frequency. So speed c, distance lambda, 1 over time, or time, which is 1 over frequency. So we have nu. So c is lambda nu. If we combine these two equations together, so we can insert nu into here, we get E is hc over lambda. We can see from this equation that energy is proportional to 1 over wavelength. Now we already know that energy is proportional to frequency. So this has some important relationships that we can use. So energy is proportional to 1 over wavelength. It's proportional to 1 over frequency. So if I look at a spectrum, spectrum just means a range of possible values. If I were to plot wavelength on the x-axis, or actually, yeah, wavelength, I guess. So if I were to look at a range of wavelengths, here we have long wavelengths, here we have shorter wavelengths. So the wavelength is the distance from a node to a reproducible, well, not necessarily a node, it's the distance from one part of a wave to the next reproducing part of the wave. So if we start here, the wave goes up. The next time that starts to reproduce is here, it goes up. So this would be a wavelength. If we look at this wave over here, the wavelength here is smaller than the wavelength here. So the time needed, or the length of the wavelength, is smaller here. So a shorter wavelength means a smaller lambda, which is proportional to a larger energy. So I know that going this way, I have higher energy, whereas over this way, I have lower energy. Roughly speaking, if you were to put a dot on every maximum and every minimum, so let's say in this part of the wave I have a dot like this, and in this part of the wave down here I have another dot. And we'll do the same for the shorter wavelength over here. Let's put a dot over here, and down here we'll put a dot. And this time we change the axis to time, the x-axis to time. Why time? Because now I'm going to look at frequency. So I've got my two dots. These dots could be particles. So I've got waves, and I can consider particles as well at the same time if I like. Now, if you were to scan from left to right as the passage of time, and each dot represents a piece of energy, count how many pieces of energy you see per unit time. So you'd reveal that piece of energy, dot, dot. So you'd reveal the two pieces of energy slowly because the wave is long, the energy is spread out. If you were per unit time, if you were to reveal the energy in the shorter wave, dot, dot, it would be a much more rapid fire of the dots. So whereas here you'd have dot, dot, here you'd have dot, dot. You would encounter the energy in a smaller time frame, so there'd be more energy density or more energy per unit time. There'd be a higher frequency of energy, a higher energy. So moving forward, this is a very important relationship, and these give you some ways to visualize this relationship.